I am so excited for the big party tonight. We should study for physics in our free time. Good idea! At the top of the stairs, I have gravitational potential energy, and as I slide down the rail, it transfers to kinetic and some energy is lost to heat.
But according to the first law of thermodynamics, all of her gravitational potential energy is transferred to kinetic energy and heat because none of it can be lost, it all just has to be transferred.
No way, Jose! Yay, let's go have fun at Emilee's house. At the peak of the Mint's arc, there's a zero velocity, but due to gravity, there's always a negative 9.8 meters per second squared of vertical acceleration. Even though Logan and I were using the same amount of weight, she was going much faster than I was. Therefore, she was applying more work. An object at rest stays at rest until an outside force acts upon it.
Alright, let's go. There's gonna be one less lonely girl. One less lonely girl. One less lonely girl. There's gonna be one less lonely girl.
As Emilee spins Carson around in a circle, she's increasing his energy, and as soon as there's a release of the force and there's no longer a force holding onto him, he travels tangent to the circle. If Carson started at a horizontal acceleration of 2 meters per second, and the ledge he was standing on was 1 meter high, how far out will Carson travel before he hits the water? So now that we know the delta x, which is 1 meter, because we measured it, and the other constant we know is the acceleration, because the vertical acceleration, or any acceleration in the vertical capacity, is always 9.8 and t squared. There's no initial velocity, because there's no initial velocity in the vertical direction, only in the horizontal direction. So if we complete this equation, it's 1 meter equals 4.9 t squared. I need a calculator. Alright, now that we've changed colors and cleverly added units, we can move our variables over to get 1 meter divided by 4.9 meters per second squared to equal our time squared. Now if we take the square root of each of those, we can find out our time to be t equals 0.45 seconds, and our units cancel out to give us seconds. Now that we have the time, we can move over and find how far he traveled in the x direction. So now we have delta x in the x direction equals the velocity, and we know that his initial velocity was 2 meters per second squared, times the time, which we have now, so 0.45 seconds, to give us 0.9 meters. So Carson traveled almost 1 meter out from the pool.
Wow, it's such a lovely day. Great day for a party, wouldn't you say? Oh! Joke's on you guys. Now I get to make awesome longitudinal waves. Woo! 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 Woo!